Okay, the very last section that we're going to cover is mass moments of inertia. Very similar again to area moments of inertia, and you'll see a lot of analogies between the area moment of inertia, mass moment of inertia, the centroid, and then the center of mass type of thing. If we look at this, our equation is very similar. We have the mass moment of inertia for I sub x around different axes, and we can integrate this. And what we're looking at is the effects of the mass about some axis. So if we look at this space station, and if we have this axis here, the y-axis, right, and if I try and spin this space shuttle around that axis, it really makes a difference whether it's real close to this axis or if the space shuttle is way out here, right? It has a lot of mass. It'll be harder to spin and harder to stop it from spinning if it's way out here. But if it's real close, it's real easy to spin. And you can also see this demonstrated in like figure skaters when they're spinning around and they put their arms out, they can slow down, but as they bring the arms back into themselves, they're lowering their center of mass and their mass moment of inertia, that they can spin a lot faster that way. So mass moments of inertia depend on the geometry of an object, right? The size and shape, and also the density of the material it is made of, and the location and orientation of where it is on the x and y and z axis. Mass moments of inertia have unique units of mass times length squared. Mass moments of inertia are also always smallest about the axis that passes through the center of mass, very similar to area moments of inertia that have the smallest value through its centroid, right? And again, this is seen and observed as you look at figure skaters when they bring themselves together. It's much smaller where if the mass is all closer to that line of axis, or it'll be much through its center of mass, excuse me. We are sometimes will omit the word mass because it's obvious that we're dealing with mass moments of inertia rather than area moments of inertia. So we kind of go back and forth between these. And as engineers, we'll know if we're talking about mass or if we're talking about area. Again, the parallel axis theorem is still related to the mass moments of inertia. The only difference is in this equation we've added in mass as opposed to area. Before we had area in there. Now we just have mass. So with that, we can then again use composite shapes, right? We can go back to these tables, use composite shapes again for finding our moments of inertia. That allows us, instead of using integration, we can use these composite shapes using, again, similar formulas that we had before. The only difference is that we have this mass term put in here for each of these. Okay? For our parallel axis portion. We'll look at an example on how to do mass moments of inertia, and hopefully that will help you understand how to do composite shapes using mass moments of inertia.